Good morning, everybody. Today we're going to be looking at nuclear decay. This is our penultimate chapter before we go on to fission and fusion. So we're going to start off by looking at radioactive decays, the kind of types that we can have, and also how we can use them to date organic or inorganic material. And then we'll plunge into the details for alpha, beta, and gamma decay. Right, so what we're talking about here is natural radioactivity. So processes that happen if the energy released is larger than zero. It has to be a net gain in the energy released. So what we've got here is alpha, beta, and gamma decay, and there are a few cases of natural spontaneous emission as well. And that's a bit like alpha decay, really. It's when a heavy nucleus splits into two fragments. And this is a bit like what's happening in alpha decay, of course. We've got a nucleus that is two protons and two neutrons being emitted from a heavier nucleus. So you can think of it like very asymmetric fission. So a nucleus emits an alpha particle. So it drops by 4 nucleons and it drops by 2 proton numbers as well. And we see that this happens for very heavy nuclei that have above sort of 200 nucleons. So if the energy released has to be larger than zero, that means that the differences in the mass of the parent nucleus and the daughter nuclei, so that's our daughter nucleus and our helium nucleus, has to be larger than zero. And this is calculated using the binding energies of the daughter nucleus, the helium nucleus, and our original parent particle. So the binding energy there is really important. So as you can guess, we'll be looking at our semi-empirical mass formula there. Then let's have a look at beta decay, and this is where a nucleus emits an electron or a positron. So here we can have a neutron changing into a proton, and along with that we're going to have an electron and an anti-electron neutrino. And so there, you want to conserve charge. The neutron is changing into a proton. So the daughter nucleus there has Z plus 1 protons, but the number of nucleons stays the same because a neutron has changed into a proton. We can have beta plus decay, and that's where a positron is emitted there instead of an electron. And this happens when a proton changes into a neutron. So again, we're not going to have any change in the nucleus's total number of nucleons, but we're going to have a drop in the number of protons as one changes to a neutron. We can also have electron capture, which is quite interesting. That's when an electron orbiting a nucleus or getting close enough to a nucleus is captured. The proton and the electron combine to a neutron and a neutrino. And so here a proton is being changed into a neutron essentially, and we have the same number of nucleons. Again, there's no change in A, but there's a drop in the number of protons. So take these three processes. Only a nucleus, a neutron is actually only the neutron decay actually happens outside of a nucleus. The proton decay and the electron capture here only happen inside a nucleus. It's only that neutron decay that happens outside of a nucleus. And finally, last but not least, we have gamma decay. And these are very high energy photons that are emitted when a nucleus drops from an excited state down to other excited states, but eventually to its ground state. Now, these photons are very, very energetic. When you compare them to the photons that are emitted from electrons as they drop down to energy levels, as they're orbiting atoms, they are very, very high energy. They're about 1,000,000 times stronger. So for an atom, you're talking about tens of electron volts for the energy of those photons, for the difference in the energy levels. But for nuclei, we're talking about MeV worth of energy. So about 1,000,000 times stronger. So instead of optical photons that are being emitted or X-ray photons, we're talking about gamma ray photons. Very, very high energy. Now you can have a slight variant on this, and this is called internal conversion. Now, where we can have an excited nucleus, it emits our very high energy photon, but that eventually is absorbed by one of the orbiting electrons in that atom. And then it's then the electron that's ejected. Now, that might look to us like beta minus emission. We've got a high energy electron coming out of our atom or our nucleus. But it's not beta decay. With beta decay, we have a change in the composition of our nucleus. A neutron is changing into a proton, or a proton is changing into a nucleus. Here, the nucleus composition is left unchanged. It's just dropping from an excited state down into its ground state. So internal conversion is when that an orbiting electron absorbs the high energy gamma ray and is then kicked out. Now, something that's quite important when we're talking about radioactive decay is the half-life. And that, as you know, is the time it takes for about half of our nuclei in a sample to decay. And it's related to the lifetime or the decay rate, and we're calling that lambda here. Now, there's a huge range of half-lives or lifetimes that we have for these nuclei that undergo decay. Some are actually comparable to the age of the Earth. They're incredibly slowly decaying. And some are incredibly quickly, fast decaying. So, for example, take this thorium here, thorium-232. We can have a look at its decay chain, and it's quite complex before it gets down to a stable nucleus. It has a half-life of around 14 gigayears. That's 1.4 times 10 to the 10 years. Very, very long half-life. And it undergoes alpha decay to radium-228. Now, radium-228 has a much shorter half-life here. It has about six and a half years, 6 to 7 years here, down to actinium-228, and then a very short half-life down to thorium-228. And this happens via beta decay. And then we've got more and more steps with various half-lives here. Got a couple of years here, down to 55 seconds for radon-220. So we have very complex decay chains and very large differences in the half-lives for different nuclei. And this is something we want to try and understand. And eventually we get down to a stable nucleus, and in this case, it's lead again. Remember, that was sitting roughly on that broad peak for the maximum binding energy per nucleon that we saw in the last lecture. So it's quite important there. When you get down to sort of lead and iron, you get to very stable nuclei. Now, let's have a quick word about geological dating. So how do we know how old the Earth is? And this is where we can use beta decay to actually tell us the age of the Earth. So we have radioactive nuclei, for example, rubium here. That's rubium-87. That's an unstable, that's a nucleus that decays via beta decay to strontium-87, which is stable. So we've just got a very simple decay chain here of just a parent and a daughter nucleus. And the half-life here is very, very long, sort of 10 to the 10 years. That's roughly the... So we can take our expressions from chapter 2 here. That relate the number of strontium we have right now in some sample to the number of strontium and rubidium that we started with at time equals 0. And we can relate them to one another using their decay rates and the time t, and that's the thing that we're interested in. So chemically, we can take a bit of rock and we can have a look at how many rubidium-87 we have here, and we can have a look at how many and the decay rate as well. So these are things we can measure, but we don't know how much strontium we actually started with here. We can't go back in time to figure that out. The solution here is to just simply normalize to another known stable isotope. For example, we could have a look at strontium-86, and that's stable. So the strontium-86 in our rock sample should be the same now as it was at time equals 0. So if we take our equation here, we normalize it, i.e. we divide through by the number of strontium-86, which we're going to call N0, we come up with a very simple straight line equation. It's going to relate the ratio of rubidium to strontium-86 to the ratio of sorry, that's strontium-87 to strontium-86, to the ratio of rubidium-87 to strontium-86, the time and the decay rate of rubidium, and then the ratio of strontium-87 at time equals 0 to strontium-86. So let's have a look at this. We can plot this. Let's try and do this properly. We can take lots and lots of different rocks, right? We can take them from the Earth, the Moon, from meteorites, and we can have a look at their strontium-87, strontium-86, and rubidium 87 ratios, and we can plot those against one another. So here we have the strontium-87 to strontium-86 ratio at time t, that's now, and we can have a look at the rubidium-87 to strontium-86 ratio as well. So this simple straight line ratio. So our y we're plotting here, and our x here is n1 over n0. And we see it's a nice straight line, as we expected, given that the gradient is based on constants, and we have a intercept here that gives us the original fraction of strontium-87 to strontium-86, and that's about 70%. The gradient here will give us the time. If we know the decay rate, we can extract the time from our gradient here. So this slope is very important, and it gives us the age of the Earth as around 4.5 times 10 to the 9 years. So by looking at lots of different samples, normalizing a decaying nucleus to one that is stable, we can have a look at the age of the Earth. And finally, we can also use radioactive dating to date organic matter, so not just rocks. And here we can use carbon-14. This is called radiocarbon dating. So if we start off in the upper atmosphere, we're always forming carbon-14 from nitrogen-14, and this happens at a roughly constant rate. So nitrogen-14 captures a neutron, and then we have carbon-14 and a proton. So basically the nitrogen-14 absorbs the neutron and kicks out a proton. Now, so carbon-14 is being made at this constant rate. That means that it enters this carbon cycle and it's exchanged with living organisms like plants, animals, etc. And any living organism is going to reach an equilibrium with this carbon-14 to the rest of our carbon isotopes. So we are vastly dominated by carbon-12. Almost 99% of us is carbon-12, and about 1% is carbon-13, and about 1 in every 10 to the 12 carbon atoms is carbon-14. So this is very, very rare. It's also unstable. It will decay via beta decay. So it will decay back to nitrogen-14, an electron and an anti-electron neutrino. And this is on a timescale of, a half-life of about 5,500 years. So when any living matter dies, it will stop exchanging carbon with the atmosphere, and the carbon-14 will be out of equilibrium and it will start to decay. And in any organic material, if it's just died and stopped exchanging carbon with the atmosphere, we're going to have about 15 carbon-14 decays every minute for every gram of carbon in that organic material. So we can measure the activity of any organic material to obtain the age of it. It gives us the number of decays per second per mass, and we can compare that to the known half-life of carbon-14 and figure out how long it's taken from whence it died and today. Now, we've kind of complicated things for ourselves with this wonderful radiocarbon dating. Since the Industrial Revolution, we've had a huge burning of fossil fuels, and it's increased the carbon-12 in the atmosphere, which changes then this equilibrium that is reached for living organisms as they're alive. We've also unfortunately done lots of nuclear bomb testing around the world, and that has significantly increased carbon-14 in the atmosphere. So this equilibrium, this known um, equilibrium that we thought we knew for carbon-14, unfortunately has a lot of complications now that we've burnt lots of fossil fuels and done all our nuclear bomb testing. But there are other isotopes that we can do radio dating with as well. So let's jump into alpha decay here. So alpha decay is one of our more simpler nuclei. It's 2 protons and 2 neutrons. It's our helium nucleus. It's doubly magic, 2 neutrons, 2 protons, magic numbers for both, and that means that it's incredibly tightly bound. What we find is that it's the most favorable nucleus to eject for many heavy nuclei. So let's have a look at this example here for uranium-232 and have a look at the energy released if it were to kick out a neutron, proton, heavy helium nucleus or tritium. And we find that the energy released is negative for all of these possibilities here, helium-5, lithium as well, with the exception of helium-4. The energy released here is positive, which means this can happen spontaneously. And we think the alpha nucleus, so the alpha particle, is actually quite easy to form within a nucleus because it's a very simple nucleus, just 2 protons and 2 neutrons. It is quite simple and it should be quite easy to form inside a nucleus. Now, this is a kind of assumption that we make throughout alpha decay when we discuss it here. You can argue about if it really does, this separate alpha particle, this separate nucleus really does exist inside an overall nucleus. You can debate that, but at the moment we're going to assume that an alpha particle has formed within a larger nucleus and then it's ejected. So when we have a look, this was done by Geiger and Nuttall in 1911. If we have a look at the half-lives for lots of different alpha decaying nuclei and have a look at the energy of the alpha particle here, E0, there's quite an easy trend here. So what we've plotted here on the y-axis is the log of the half-life against the energy here. And there's a very strong dependence between the lifetime, the half-life, and the energy of the alpha particle. So take thorium-232 here. It's sitting up here. It's got the alpha particle that it releases is around 4 MeV, and its half-life is huge. We've said that before. It's about 1.4 times 10 to the 10 years. What, about 14 gigayears here. Absolutely huge. But if we go down to thorium-218 here, the energy released is about double that of thorium-232 at around almost 10 MeV. But the half-life is hugely different. It's 10 to the minus 7 seconds here. So we've got roughly a 2.5 times increase in the energy of the alpha particle released, but a factor of 10 to the 24 in half-life. This is absolutely huge. So we need to try and explain this. What is this strong dependency that we're having here? So this is a common thing in when we have a look at radioactive decay, but what we're going to do is have a look at alpha decay, using tunneling. So we're going to start off within the radius of a nucleus here, R, and we're going to say our alpha particle has already formed within the nucleus. That's debatable, of course, but it's formed within the nucleus. However, to escape the nucleus, it has to overcome this Coulomb barrier. Now, of course, classically, it's not going to be able to do that. It's sitting at energy that's lower than this Coulomb barrier, but quantum mechanically, of course, it can tunnel through. And at the point that it's free, we'll call that R dash here, R prime. At the point that it's free, it's tunneled through this barrier. So we're going to have a look at this as a tunneling problem. One assumption we are going to have to make, and it's a big assumption, is that this alpha particle already exists inside of the nucleus. And it's roaming around trying to tunnel through the Coulomb barrier. It's trying to escape. And its decay rate, the rate at which it's going to be able to escape, is going to depend on how many times it's going to try and escape, its escape trial frequency, and the probability that it has for each of those times to actually tunnel through. We're going to treat the escape trial frequency semi-classically. Here, it's going to depend on the velocity of that alpha particle. So it's going to depend on the mass, and it's going to depend on its energy, and it's going to depend on the radius of our nucleus as well. So typical values here, the potential for our Coulomb potential there is around 35 MeV. The energy released for that, the energy of the alpha particle when it escapes is about 5 MeV. That means that it's got to have about 40 MeV inside our nucleus to escape there for the escape trial frequency. So this is semi-classical. We could obviously improve upon this. So it's going to try and escape around 10 to the 22 times per second. Very, very high here. So we've got the mass of the alpha particle we've plugged into there and the average mass of a nucleus at 2.1 femtometers. Next thing we need to do is have a look at this tunneling probability here, and we're going to have a look at this using the Schrodinger equation, of course. So let's consider a 1d squared barrier for the Coulomb potential. You've seen this many different times before through quite a few courses, quantum physics, your quantum mechanics courses, and your AQM. And the transmission probability is going to depend on the potential that it sees, the difference between its energy and that potential that it sees as well, and also its mass as well. So since we're talking about very small distances, the probability for escape is actually going to be dominated by the exponential decay of this potential within the barrier. So it depends on how this Coulomb potential decays. So that potential decays throughout as R increases here. So that's really important. So we can calculate then, we can just simply integrate over this Coulomb potential over the distance that it's going to experience. This is our Gamow factor. It's going to depend on the potential at some distance R as it's tunneling through, the energy of the alpha particle, and the radius as well. So we can do that integration. Now, as the alpha particle goes beyond the radius of the nucleus, it's going to experience that simple Coulomb potential. That depends on, of course, the charge of the alpha particle, that's 2. The charge of the daughter nucleus, that's whatever you started with, -2. However far away and however far those two nuclei are separated. We can then encapsulate those charges there as B. So if we say, if we go back here, that our alpha particle escapes at R prime, the potential that it sees there at R prime is E0, and we can then replace there in our Gamow factor the point at which it escapes. R is going to integrate over between R and R prime there as B over E0. You can have a look at this integration here. It's done in Appendix H. But there's a nice simplification that you can do afterwards because usually the radius of a nucleus is much, much smaller than the escape radius, R prime here. So we can get rid of this term here. And this cosine, inverse cosine term here goes to pi over 2. This simplifies our Gamow factor quite a lot. This Gamow factor, remember the probability is going to go as e to the -2g here. So this Gamow factor is containing all the information. It depends on the square root of the mass of the particle that's being ejected, this alpha particle. It depends on 1 over the square root of its energy, and it depends on B here, which remember is the describing the Coulomb potential, the charge of the alpha particle and the daughter nucleus. So if we had a typical nucleus with 90 protons, a alpha particle that's emitted at 6 MeV, and its escape radius, that means that its escape radius is about 40 femtometers. That's quite a lot it's got to tunnel through here. So does this explain our strong dependence between the half-life or the lifetime and the energy of alpha particles? And indeed it does. We can take the lifetime of our particle as 1 over the decay rate. We've said our decay rate is the trial frequency, which we've treated semi-classically, and the probability of escape, which we've treated as a quantum mechanical tunneling problem. And so we've got our 2r over v here for our trial frequency and e to the 2g here for 1 over our probability. If we take the log of both sides, we can quite easily see that we have a dependence for the decay rate. The log of the decay rate goes as the charge of the daughter nucleus over the square root of the energy released. So it's not an absolutely perfect explanation here. You can see if we, for example, if we plot the log of our decay rate against the charge of the daughter particle and the over the square root of the energy released, we get roughly a straight line. In fact, most of the points sit very, very close to this line. But we get a very good explanation of why we have this strong dependency between the lifetime or the half-life of our alpha decaying particles and the energy of that alpha particle. So this is the Geiger-Nuttall law, and you might have seen in many different tripos exams. It used to be a favorite for brief notes, for example, and I will be asking you to write a brief notes explanation of the Geiger-Nuttall law in your problem sheet 4. Now, this is a very simple approach that we've taken for the trial frequency and the probability here, and it does account for our strong dependency. It's quite good. We're definitely seeing that our half-life increases with the number of protons in a nucleus, and it's also explaining why we don't have decays to heavier fragments, heavier than a helium nucleus, 2 protons and 2 neutrons. So this gamma factor that we calculated here is proportional to the mass of the emitted particle, the square root of the mass of the emitted particle. So the larger the mass of the emitted particle, the larger the gamma factor, and the higher the lifetime. So as long as it's light, it'll keep the lifetime shorter, and it'll therefore happen sooner than heavier fragments. It's also, this gamma factor is proportional to the charge, by this constant B, is proportional to the charge of the emitted fragment here, Z alpha. And so if we have heavier fragments, they've got a higher number of protons, they'll have a higher charge, they'll also increase G, and they will increase the lifetime. So lighter fragments and fragments with a smaller charge are preferred. Now, this is a simple model. It has its deficiencies, and of course, we could maybe add some complexity to our model to try and overcome this. So, as I said at the beginning, we have assumed that an alpha particle already exists inside that nucleus and not said anything on how that was actually formed or the probability of its formation as well. So things like that might affect the decay, the lifetimes or the decay rates here of these particles, moving them off that simple line that we came up with here with the Geiger-Nuttall law. We've also assumed this semi-classical approach for this escape trial frequency, which isn't fantastic. Ideally, we would have a purely quantum description for that as well, and that would allow us maybe to make a more precise prediction of our decay rate. And then finally, sometimes the alpha particle has to be emitted with some angular momentum. And that if that happens, we're going to have a an increased barrier, not just the Coulomb barrier that the alpha particle is going to see. It's going to have an increased barrier from this centrifugal barrier because it's emitted with higher L. So if it's emitted with L equals 0, this extra potential that it sees is 0, but it's emitted with L larger than 0, it's going to increase the barrier and then suppress that decay. So what we find is that alpha decay usually only happens in low L states or L equals 0. So finally, for alpha decay, let's have a look at the selection rules. Now, the nuclear shell model tells us that the alpha particle is spin 0 and positive parity. It has 2 protons and 2 neutrons. It's an even nucleus, so it's quite an easy one to remember. Now, if you consider some parent particle is decaying to the daughter particle y, so x is going to y plus our alpha particle, this then limits the angular momentum values that x and y can take. So we have to conserve J, of course. Remember, this is one of our strict quantum numbers, and the angular momentum of x has to be the sum of y and the alpha particle. Since this is a spin 0 particle, it depends on the orbital angular momentum that it's emitted with. So the orbital angular momentum of our alpha particle then, therefore, since we've got to conserve J, it can take values of anywhere between the difference and the sum of the two, the parent and the daughter nucleus. What about the parity? The parity depends on the orbital angular momentum that alpha particle is emitted with. So if our parent and daughter nucleus both have the same parity, that means, of course, that we're going to have an even parity alpha particle, i.e. its L is even. If they've got opposite parity, flip that on its head, it means that we're going to have an odd parity alpha particle and its L is odd. Now, if we have both of these nuclei, they're both even nuclei and they're in their ground states, they should both be 0 plus. And that means that we can only have an L equals 0 nucleus because it can't, if it's going to carry away any angular momentum, we can't have 0 to a J equals 0 to a J equals 0 state. So there's a general rule here that if you're starting off with a spin 0 positive parity nucleus and it's undergoing alpha decay, the states that you can form for Y are going to be 0 plus, 1 minus, 2 plus, 3 minus, and 4 plus. I.e., if there is the same parity between this daughter particle and its parent particle, 0 plus, we're going to have an even parity, sorry, an L equals an even L for our alpha particle, so it can be 0, 2, or 4, etc. And then if we're going to have a parity change from plus to minus here, then we're going to have odd numbers for L. Okay, so let's move from alpha decay into beta decay. And as I said a few slides ago now, there are 3 main types. There's beta minus, beta plus, and electron capture. Now, remember back in the particle part of the course, we had a look at neutrons changing into protons, and we had a look at this on the quark level. And these are weak decays mediated by that massive W boson, and they can violate parity. So let's not worry too much about parity in these beta decays. And this was actually the process that was responsible for Fermi for actually postulating the neutrino. Let me just change what I'm presenting here. There we go. Share. Right, so when all the way around, when Fermi was having a look at beta decay, he was plotting the energy of the electron or positron that was coming out, and he found that it looked something like this. And he was expecting, so this was what he saw, and he was expecting from a proton to, for example, a neutron and a positron, he was expecting a single energy uh, for our positron here. For one particle decaying into two, you're just going to have um, a single energy for your possibilities, for your neutron and your positron here. But what he saw instead was a spread of energies, which suggested that it was actually a 1 to 3 decay, not a 1 to 2, i.e., that your proton is decaying to a neutron plus a positron plus an electron neutrino there, and instead the energy has to be shared equally amongst three. And therefore, you're going to get a different density of final states, a different set of energies here that we can have for our electron. And so this is what made him realize that there had to be something else in the decay. There had to be this third particle, something very invisible, the neutrino. Okay, so it's the same thing here. If we have natural beta decays, they're only going to happen if the energy released is larger than zero. And we can have a look at the energy released here in terms of the nuclear masses, just taking into account the differences in the number of protons and neutrons and the electron or positron as well. You can add in the neutrino mass, but that is effectively zero. Or you can have a look at the atomic masses. And this is where you've got to be careful at the change in the number of electrons, because we're talking about neutral atoms here. So if a nucleus undergoes beta decay and an electron is emitted from the nucleus, there's also going to be a gain in the number of by one of the orbiting electrons to make the nucleus overall, sorry, the atom overall neutral, because the number of protons has gone up. If you look at beta plus decay, a positron is being kicked out of the nucleus, and your a proton is changing into a neutron, and so an electron is also kicked out of orbit to give us an overall neutral uh, atom. So this is why we don't have the subtraction of the electron energy here, because it's essentially accounted for in the gain of the electron in orbit. And we have to subtract 2 here because we've got one being kicked out of the nucleus and one being kicked out to make it a neutral atom. And then for electron capture, here for the nuclear mass, we're adding an electron. We're not kicking something out, we're adding an electron here. And it's the same. It's similar for the atomic mass change as well. We're adding an electron. We're changing a proton into a neutron in that way. So there's no overall change in the electrons for the total atom. Now this is quite interesting because we can change a proton into a neutron here via electron capture, but maybe not via beta plus decay. If you have a look at the energy released, either here for the atomic or the nuclear masses, it's greater for electron capture. So sometimes we can have electron capture is possible, but beta plus decay is not. Now let's have a look at our good old semi-empirical mass formula. What's happening for our nuclear masses as they undergo beta decay? So let's have a look at our semi-empirical mass formula. We have the number of protons, the number of neutrons, we have our volume term, our surface term that decreases the binding energy because they're less tightly bound on the surface. We have a Coulomb term that depends on the number of protons. We have our asymmetry term that tries to keep the number of protons and neutrons roughly equal. And we have our pairing term as well. Now, when a nucleus undergoes beta decay, the number of nucleons, protons plus neutrons is constant. A proton is changing into a neutron, or a neutron is changing into a proton. But the number of protons is changing either up or down by 1. So if we want to have a look at the terms that are going to be affected here, it's obviously our number of protons and our number of neutrons. Our volume and our surface terms don't actually depend on this, they'll be the same. But our Coulomb term and our pairing, our asymmetry and our pairing term will be affected. Our pairing term is completely empirical anyway, but both of these terms depend on z squared. We've got terms that depend on z here, and we've got terms that depend on z squared. So we actually have the mass of a nucleus, whether before and after it undergoes beta decay, it's quadratic in z. So we've got terms that depend on z and terms that depend on z squared. Now, the most stable nucleus for if it's going to undergo beta decay is going to be when this is minimized. Our mass basically is minimized. It'll undergo beta decay until it reaches the minimum mass that it possibly can. And this is going to be our most stable nuclide. So let's have a look at this. So the two situations that we have depend on how many nucleons we have. So let's say we've got an odd number of nucleons, so either an odd number of protons or an odd number of neutrons. We can undergo beta plus decay and decrease the number of protons here until we get to our stable point, and that's our point of lowest mass. And basically that increases our binding energy and gives us the lowest mass that we possibly can. If it's beta minus decay, if we're starting off up here, it'll increase the number of protons until it stabilizes and really gets to the most stable, i.e. the highest binding energy, lowest mass particle that it possibly can. It's a slightly different picture if we have an even number of nucleons, because if we have an odd nucleus, odd number of protons and an odd number of neutrons versus an even nucleus, which is even both, they're going to get a difference in the pairing term, which is going to change our binding energy and change our overall mass here. So a heavy nucleus here will start off maybe with too many protons and undergo beta plus decay and bounce between odd and even until it reaches the lowest it possibly can, or it'll undergo beta plus minus decay here, increasing the number of protons until it reaches the most stable points. Now, usually what we have are two stable points on this overall minima, because the pairing term here means that the binding energy is not very large compared to these two. So the pairing term does matter. So we have two stable isotopes here. Sorry, we have two stable points here if we have an even number of nucleons. So what we're going to do here is model beta decay using Fermi theory. Now we can use Fermi theory because we are in a very low energy regime here. So remember we said that this 4 fermion contact interaction mediated by some described by some effective coupling constant here, GF, was only valid in low energy. It was only a low energy approximation of some higher order theory, which was the weak theory. And that was the one that was propagated by that massive W boson with the coupling strength GW. So we are in a low energy regime here. We can happily use Fermi theory, which simplifies things quite nicely. And we can use Fermi's golden rule to have a look at the transition rate here. So this is what we're going to do next. I need to stop presenting. This is what we're going to do next. I will go through this. Let's add a new page. Right. Right. So what we're going to try and do is understand, we're going to use Fermi's golden rule to have a look at the decay rate for some particle X changing into Y, an electron and an anti-electron neutrino with strength GF. So this is relatively straightforward. We're going to use Fermi's golden rule, of course. 2 pi times the matrix element squared multiplied by the density of final states. I'm going to start off with the matrix element, our wonderful matrix element here, and this is a four-point interaction. So we can write this matrix element as this coupling GF. It's coupling GF, and it's going to depend on the neutron wave function, the proton wave function. I'm doing an example, by the way, for a neutron changing into a proton. The electron in the final state and our anti-electron neutrino in the final state. And we're going to integrate this over all space. Now our electron and our antineutrino are free particles. They're quite easy. So we can, for example, we can just write their wave functions as e to the minus p dot r. So it depends on the momentum of the electron. But the proton and the neutron are not free particles. They are in bound states, and we need to take that into account. So this can be written, we've got our proton wave function, our free particles, our electron and our neutrino, plus p nu dot r, and phi for the neutron, integrated over all space. Now, this is quite complex. The wave function of our proton and our neutron is going to depend on that very complex bound state that they're in. They're not going to quite behave like free particles, and they're not going to quite behave like they're in rigid states. So I'm going to try and summarize all of this as some nuclear matrix element. I'm going to simplify it like that. So there's still a bit of a question mark because of the complexity over the matrix elements. But we can start to have a look at the density of final states. That's quite straightforward here. Now this time, let's do density of final states. This time we have a three-body final state. Back in chapter 2, we had a look at one particle decaying into two, and we could have a look at the density of final states by just having a look at what one of those particles could take in terms of energy, and then we could use energy conservation to find the other one. So we just needed to know about one. And we're going to do a similar thing here, but here we have to take two particles as independent, and we can find the third by having a look at the energy and momentum conservation again. So this is one particle into three again. So we've got a three-body final state. So we're going to treat two as independent. And we can have the third from energy and momentum conservation. So let's have a look at this. I'll try and keep my writing a little bit neater. Sorry about this. Our density of final states, dn, the number of final states that we can have, depends on, what I'm going to do is our two independent particles. I'm going to have a look at the electron and the neutrino here and assume that we can find, and of course we can find, the energy of that daughter nucleus by energy and momentum conservation. So we can write down the term for our neutrino, 2 pi cubed, integrated over the solid angle, and integrated over the momentum. So go back and look at chapter 2 if this seems like an absolute foreign thing to you. Now we're going to need to have a look at the electron as well as the neutrino. They're both independent of one another. So we're going to need to multiply this by the number of final states that the electron can take, of course. And it's exactly the same term, but for the electron. Integrated over the solid angle and integrated over the momentum of the electron. So let's try and understand this. The energy released is going to go into the kinetic energy of our final state products, our electron, our neutrino, and our final state nucleus. So this energy released is going to be the neutrino energy, the electron energy, and also any recoil from the nucleus. Now this I'm going to approximate as roughly 0 because the nucleus is much heavier than the electron or the neutrino. I mean, that's basically massless, isn't it? So we can approximate the energy released as the neutrino energy and the electron energy. Now let's have a look at the density of final states for a given electron energy, and then we can integrate over all electron energies. So for a given electron energy, the change in the energy released is just going to depend on the change in the neutrino energy. And since they're basically massless, we can approximate this as the change in the neutrino momentum. So if we take this density of final states and differentiate it according to dE0, i.e. we're going to just take this term here down there because dP is dE. We can rewrite this, dP nu, the energy of the neutrino squared over 2 pi cubed, depends on the solid angle, the electron momentum squared, we've got the 2 pi cubed, d sigma, sorry, d omega, dP. Next thing we want to do is integrate over our solid angles. For both of these, and we're going to assume it's an isotropic decay. So we're going to have our 4 pi coming in here from each of those. Right, so our dN, dE0, this is our density of final states that we're looking for. We're going to get 2 factors of 4 pi coming from the integration over these 2 solid angles. We've got our energy squared, we've got our 2 pi cubed, oops, still. We've got the electron momentum over a 2 pi cubed still, dPe. And so we can have some cancellation here between all of our factors of 2 pi to simplify as EV squared, or E nu squared, PE squared over 4 pi 4 dPe. We can simplify this a little bit more. For example, we can take the mass of the energy to be roughly 0 so that its energy is roughly its momentum. And we can rewrite this as E nu squared, E squared over 4 pi 4 dE. And we can replace this energy of the neutrino here by the difference between the energy released and the electron energy. So E0 minus EE squared over 4 pi to the 4 EE squared dE. And so this is the beginning of Sargent's rule here. If we put all of those pieces together, and you can have a look at a slightly neater version of the worked examples on the website. Where are we? If we put all of those together, let's change our windows, get something a little bit neater. We will have that our decay rate goes as our GF squared and our nuclear matrix element squared. So that's the bit that contains those two free particles, the electron and the neutrino, but also the wave functions of our proton and neutron, which are quite complex. And then from the density of final states, we have an integration of the energy released minus the electron energy all squared times the electron energy squared, and integrated over all energies that the electron can take. And that can only be from it gets zero kinetic energy, or it gets all of the kinetic energy, all of the energy released. So it can only go from 0 to E0. If you do this integration, you'll come up with Sargent's rule. So this is the proof of Sargent's rule. When you have a look at the Fermi theory of beta decay, you're taking a look at that 1 to 3 body final state. If you have a look at the density of final states here for our 3 body final states, you can come up with Sargent's rule. So the decay rate is going to be proportional to the energy released to the power of 5. So that's where that comes from. Click on it. Right. Now, if we plot the Sargent's rule, sorry, no. If we have a look at the energy of our positron or our electron in beta decay, and we plot this over the square root of the rate of change, the differential decay rate over 1, okay, it's easier here. If we plot the energy released here against the square root of the differential decay rate times 1 over the momentum of the electron squared here, we should get a straight line. This should be proportional to the energy released minus the electron energy. It should be proportional to the neutrino energy. Now, interestingly, we can measure the total energy released in beta decay without even measuring the neutrino energy, because the endpoint of this interaction here, the maximum energy that an electron can actually take, or a positron, is going to be when it takes all of the energy that's released in the interaction. So we can have a look at these plots. These are called Curie plots. And for this example here, we have tritium undergoing beta decay into helium-3. And for that, it's going to take a neutron, change it into a proton, and kick out an electron and antineutrino there. And when the electron takes all of the energy released in the interaction, about 18 keV here, we can measure the energy released there. Now, it's not that simple. Of course, it's not that simple. When an electron or a positron is emitted from the nucleus, there's a Coulomb interaction, of course. A positron will be repulsed by a nucleus because they've got like charges, and an electron is going to be feel more of a tug back towards the nucleus because they have different sign charges. So we can take this into account, and we can have a look. We can plug this into our decay rate that we just calculated as a Fermi function that's going to depend on the charge of the daughter nucleus, and it's going to depend on the energy of the electron as well. So it's very much a function of the density of final states here. It's where we need to include it. Now, this is quite a complicated integral, and values for this so-called Fermi integral are tabulated. You can look those up. But what's quite interesting is if we have a look at this Fermi integral, I'm going to call it little f here, multiplied by the half-life. And so the half-life here is log 2, 1 over the, sorry, log 2 times the lifetime. And the lifetime, of course, is related to the decay rate. So what we can do here is if we have a look at the Fermi integral and the half-life of any beta decay nucleus, we can then maybe get some insight into this nuclear matrix element, the one that contains the, yes, easy free particles of the electron and neutrino, but the proton and the neutron wave functions as well are complex because they're in a bound state. So what we can do is have a look, measure our half-life, multiply it by the Fermi integral, and maybe have an insight onto this matrix element. So this is what this looks like. The number of cases is on the y-axis, so i.e. the number of nuclei that give us these particular values of the comparative half-life f tau. What we find is that there are some that sit with very low comparative half-lives here, and these are known as super allowed. They appear actually to happen very quickly. The bulk of them here seem to sit between sort of 4, 6, and 7-ish, this sort of orange area here. These are known as allowed. And then there are some here with very large comparative half-lives, sort of above 6 or 7, and these are known as forbidden. And we'll try and understand that with respect to the matrix element, the nuclear matrix element. So let's have a look at this nuclear matrix element again. It contains our free particles, our electron and our neutrino. That's easy. But our proton and our neutron are not so easy. So it's the neutron in the initial state and the proton in the final state. Now, we can make maybe have some insight here that our allowed transitions, these ones making up the bulk of all of these cases that we actually see around the comparative half-lives of about 4 to 7, are when the electron and the neutrino are released with zero orbital angular momentum with respect to the nucleus, i.e. they're not taking away any orbital angular momentum. And that means there the momentum, or P dot R, is 0, and this exponential then is 1. So this part here, this exponential basically goes to 1 for our allowed transitions. For our super allowed transitions, those that have even smaller comparative half-lives, we find that this is usually the case for mirror nuclei, where we have our proton and our neutron with a very similar wave function. And that means that the rest of the nuclear matrix element, not just this exponential here, the rest of it is roughly 1 as well, if their wave functions pretty much overlap. Right, so it depends now on what kind of allowed and these super allowed transitions we can have. It depends on the spin of the electron and neutrino system. They're both fermions, so they can be released with spin 0 or spin 1. Now let's have a look at these allowed transitions and super allowed where they're not released with any orbital angular momentum, so L equals 0. Let's have a look at what we can get. So what we're going to look at here is the case of some nucleus decaying to another one, emitting an electron and an anti-electron neutrino. So X going to Y plus this electron and neutrino pair. We need to conserve J. So the angular momentum of the parent nucleus is the angular momentum of the final state nucleus, and then it depends on the spin and the orbital angular momentum of the electron and neutrino pair. So we're going to do this for L equals 0. That way we're trying to maximize this nuclear matrix element. We're maximizing the we're trying to maximize the wave functions and the nuclear matrix element in general. So what happens if the spin of our electron and neutrino pair is 0 versus 1? So what I'm going to do is leave this share, and I'm going to share another window and draw this out for you. Nope, not that one. There we go. We add a page. So we have some particle X decaying to Y and our electron neutrino pair. We know we've got to conserve J. So the angular momentum of the parent particle X is equal to the sum of our daughter particle and our electron neutrino pair. And we're going to be doing this for L equals 0. Now there's 4 different spin states we can have here. So let's have a look at the first lot. So the electron and neutrino are in an antisymmetric spin state. And that will give us S equals 0. So I'm going to look at an example where we've got a neutron going into a proton. And then we've got some superposition of a couple of spin states here. Try and make this clear with the spins in red here. Right. If the spin of our neutron is originally pointing upwards, so fermion, and we're looking at a spin 0 state here, so we've got up, down, or down, up. That means that our proton is going to be pointing spin state in the same direction as the neutron here. So we've got, oops, right. Let's have a look at the magnetic spin quantum numbers here. Here we have an ms of plus a half. Here we have an ms of plus a half. And this is s equals 0, so we can only have ms equals 0. And we're doing this for an L equals 0 state for the electron and neutrino. That means that ML also has to be equal to 0. Thus, the J here of this electron and neutrino system has to be equal to 0. You've got a delta J of 0. There is no change between the total angular momentum of the initial and final state particle. And since it's an L equals 0 state here, there's no parity change either. Right. The next one we can have a look at is the electron and neutrino in a symmetric spin state. Right. And this is going to be where we've got the spin is 1, and our ms values can go from can be -1, 0, or +1. Right, we're going to have a look at the neutron and proton and the electron and neutrino again. So our neutron decaying into our proton. And here I'm going to have a look at the superposition of the electron and neutrino in 2 different stabilities here. Have a look at their spins. We're looking at up, down, and down, up. Here we've got the symmetric possibility. If we start off with a neutron pointing upwards, we're also going to have a proton in the same direction. So again, ms equals a half here. We're looking at SE nu equals 1, and an ms equals 1 for our electron and neutrino state, from an L equals 0 and an ML equals 0. Therefore, this proton has to be ms equals plus a half. Right, so again, here we're going to have delta J equals 0. But there's a caveat here. We can't have 0 to 0 decays. Forbidden. We can't have 0 to 0 decays here. And that you've definitely seen in other courses, and I've been asked by some of my supervision students as well. This is one of our basic selection rules here, that when you have such a decay where the one of your states is spin 1 here, we can't have a state 0 going to state 0 given an LE mu equals 0. So we could have this type of decay with a 0 change in the total angular momentum between x and y, but as long as they have a non-zero value of j. Right, and the final example where we've got the neutron going into a proton, and we have a symmetric spin state here. Let's have a look at our electron neutrino. I'm going to give the example of up here, so that if our neutron starts in an up state, then we're going to have the proton has to flip the spin here. So you can imagine the opposite way. The neutron starts as a downward, it will change into a proton with an upward spin, and this would give us our down-down version. All right, so let's have a look at our quantum numbers here. I've done ms equals plus a half here, and we've got minus a half for our proton here. For our electron neutrino system, we've got spin 1 and ms equals plus 1. You can do the same for minus 1 if you want. And it's still an L equals 0 and ML equals 0 that we're having a look at for these allowed decays. And so here we're going to have a change here of delta J equals plus 1 or minus 1 if you have a look at these. So the change in your, can I decrease this? The change in the total angular momentum between x and its daughter particle y can be plus or minus 1 here. And you will also, will be plus or minus 1 here. So there's 3 possibilities that you can have here. I'll try and do it in blue. No. All right. You can have a delta J of 0 when you have an anti-symmetric spin state. You can have a delta J of 0 if you have a symmetric spin state here, but 0 to 0 is forbidden. And you can have a delta J of plus or minus 1 here. And these are so-called Fermi transitions, when you have a spin 0 electron and neutrino state given off. Or you can have these two are called Gamow-Teller transitions here. So these are the 2 types. Either a spin 1, a symmetric spin state for the electron neutrino is emitted, you have a Gamow-Teller there, or a spin 0 state is emitted, and that's our Fermi. There. Right. And in all of these cases, the parity of the nucleus is completely unchanged. That's because we're considering the case where we're considering the cases where the electron and neutrino are emitted with 0 orbital angular momentum, with L equals 0. So there cannot be a change in the parity of the nucleus, this parent and daughter nucleus. There cannot be. Okay. So those were the allowed transitions, Fermi or Gamow-Teller allowed transitions. Next, let's have a look at our forbidden transitions. And we're going to attribute these to when the electron and neutrino are given off with some non-zero angular momentum, and that will suppress the decay. So these, we call them forbidden transitions, but they're not forbidden. They're just suppressed with respect to the L equals 0 transitions. So we can take our electron and neutrino wave functions here, and we can have a look at an expansion of this in increasing terms of the momenta dot r. So when they're emitted with L equals 0, the sum of their momenta dot r of that system is 0. So this is essentially 1. So these allowed transitions will dominate. So the parity there of the emitted, well, it's an L equals 0, of the emitted electron and neutrino is even. Now, if we have a look at the first forbidden decays, these are for L equals 1. With increasing L, we get increasing levels of forbiddenness, simply because we have an increased potential, essentially, that the electron and neutrino system will see to overcome during the decay. So the first forbidden ones, because they are emitted with L equals 1, you're going to have a parity change there, because we can have a parity change, the others as well, but it'll go back to even. You can, because it's carrying away an odd number of angular momentum units, you will have a parity change. And then for the second forbidden, because L equals 2, you're not going to have a parity change, but you will have an increased level of suppression here. So in general, the lowest order of nth suppression is going to dominate. So if you can't have an L equals 0 or an allowed transition here, maybe you can only have a Gamaltella transition and you're starting off with a J equals 0 state to a J equals 0 state, and that's not allowed. Maybe the first forbidden ones would be allowed. So what we're going to do to try and make this absolutely clear is go through a few examples, and this will, I think, clear up some of this when you see it in action, clear up some of the common questions about nuclear decay. Am I presenting the right thing here? Yes, right. Right. Ooh. What we're going to do is have a look at what we're going to do here is have a look at chlorine 34, and that going to sulfur 34. It's a very good practice in remembering all of my chemical elements. And this is a 0 plus state going to a 0 plus state. So immediately you know that Gamaltella is not allowed, because you're going from a 0 plus to 0 plus. Now we can see that there's no parity change. The first thing we want to check is the parity. There's no parity change, so we know L equals even. We know we've got an even L for that electron and neutrino system. We've also got no change in J. So what are we allowed there? When you go back to slide 26, we have no parity change, so we can have an allowed transition here. And there's no parity change. There's no change here. We know that we have to have a spin 1 nucleus here. We're going to have, sorry, I've written the wrong thing. So 0 to 0 is forbidden, and we don't have any parity change. That means that we're only allowed a Fermi transition. Okay. So if we have a look at the other ones that we could have, for example, the Gamaltella, we can't have the the Gamow-Teller, since delta J equals 0, we can have delta J equals 0 or delta J equals plus or minus 1. We can't have delta J equals 0 because we've got a 0 to 0, and the change in J here is not plus or minus 1. So we know that it can be an electron neutrino spin 0 system, and it can be a Fermi transition. And we know that it could be, since there's no parity change here, it can be allowed. So the allowed decay here for this beta decay, it can be a Fermi decay, and it's allowed, not first suppressed or sorry, first or second forbidden or something like that. The next example we're going to have a look at is carbon-14 undergoing beta decay to nitrogen-14. Sorry, nitrogen-14. And this is a 0 plus state going to a 1 plus state. So let's have a look at the parity. So there's no parity change, where we know we've got even L. We can see that there's a change in J of 1, plus 1. And the only type of decay that can do that, it's not the Fermi transition. The delta J there is 0. There's two possibilities for Gamow-Teller, where the delta J is 0 or the delta J is plus or minus 1. So we know that this has to be a Gamow-Teller decay. And since L is even, we can say that this is a Gamow-Teller allowed decay. See, it's this simple. The next thing we're going to do is have a look at a neutron. Let's keep this very simple. A neutron going to a proton, and its spin half positive parity going to a spin half positive parity proton. So there's no change in parity again, so we know there's no change in P. So we've got even L again. And we know that delta J here, it's both a half. So there's no change in J here. So there's two possibilities we can have here. We can have Fermi allowed, and we can have Gamow-Teller allowed as well, because we're not in the 0 to 0 state. Yeah, it's a non-zero value of J we can have. And actually, this could be super allowed. We're not told this, but if the neutron and the proton are in mirror nuclei and they're sitting in the same shell in the nuclear shell model, they'll have the same quantum numbers, and their wave functions will maximally overlap, and it will push your nuclear matrix element to higher values. So this could be a super allowed decay. So be careful when you're looking at some decays which can be from mirror nuclei. They can be super allowed. I'm next going to have a look at argon-39 going to potassium-39. And this is a spin 7/2 negative parity state going to a spin 3/2 positive parity state. So there's a parity change here. We know it can't be an allowed decay. There's a parity change here. So L is larger than 0, and actually L is odd. So we know it's going to be some forbidden decay. So we're looking at something, one of the forbiddens. We've got a change in J of 2. So let's have a look at what we could have. Let's have a look at the first forbidden. If we had an L equals 1, so we are going to try a first forbidden, we could have our electron and neutrino system be emitted with spin 1 and give us a Gamaltella decay. And that would give us the delta J of 2 if these two essentially add up to 1. We can't have Fermi transitions because the spin of the electron neutrino system will be 0 and won't give us a delta J of 2. So here we would say that this is a Gamaltella decay, a Gamaltella, first forbidden. And finally, my final example here is 87, rubium 87, going to strontium 87, that wonderful example that we had a look at earlier for the um, radioactive geological dating of rocks. We've got rubidium 87 going to strontium 87. And this is a spin 3-2 negative parity state going to a spin 9 over 2 positive parity state. So we've got a change in parity. We know that L is odd, and we're going to be looking at some forbidden decay. We've got a large change in J here. We've got a delta J of 3 this time. So let's have a look at the types of forbidden that we can have. Let's start off with the first forbidden, and L equals 1. Now, since that we can only have, even if we had Fermi or Gamaltella here, of 0 or 1, that's not going to work. That's not going to give us a delta J of 3. At no point do they add up to 3. Let's try the next odd forbidden, and L equals 3, because we know it's got to be odd, because there's a parity change. Can't have 2. So L equals 3, we can have the electron or neutrino system to be spin 0 or 1. Either of these would work to give us a delta J of 3. So here we would say that this is Gamaltella or Fermi, and it's a third forbidden decay. So you would expect this final example here to have a very long comparative half-life compared to the allowed decays, simply because it has to go through a decay where the electron and neutrino are emitted with quite a high value of orbital angular momentum, which suppresses the decay. Right, let's move on. Okay. So let's move on to the last but not least is gamma decay. And so, as I said at the beginning of this long lecture, we see gamma decay when we have a nucleus going from an excited state down into its ground state. This happens very often, actually, after we have alpha or beta decay. That daughter nucleus is produced in an excited state, and it will go down into its ground state via gamma decay. So we've got some initial state here sitting at higher energy, some excited state, and it drops down to the ground state or some way along the way via the emission of a photon. Now, these are bosons. We're not dealing with fermions anymore. They're bosons. They are spin 1. They're going to carry away some net angular momentum. So there's going to be some change here in J. So our photon is carrying, well, the photon, we've already said this in part of the particle course, it's spin 1 and it's negative parity. Therefore, the orbital angular momentum is going to be larger than or equal to 1. It's going to change the parity of a nucleus. And the difference between the initial and final state J's here can go from, is going to be lower than or higher than the orbital angular momentum of our photon that's being released, simply because of the conservation of J here. Now, you can go back to your selection rules as well. we cannot have gamma decay from an initial state which is spin 0 or j equals 0 to a j equals 0 state. This photon has to carry away orbital angular momentum. It cannot do that if the initial and final um, states are both j equals 0. If it's going to carry away some orbital angular momentum, it has to carry some away with respect to something. If you think about that, it has to start rotating around something. Now, the energy of these photons are much, much higher energy than those of the atomic transitions. These are happening over much, much smaller distances. So you can think about these photons as probing over much, much shorter distances, being smaller wavelengths, and thus higher energy. And this is happening on much smaller distances, at much smaller timescales. So these transitions happen at much higher rates than the atomic transitions that you're used to. Now, when you had a look at the atomic transitions, you saw that only the dipole transitions were important, and you didn't really go any further than that. But now with nuclei, we are talking about quite complex systems where we don't just have fundamental particles, we have a whole collection of them. We've got protons and neutrons here. And these can lead to higher transition types being more important. So we won't just be looking at dipoles here. Now, there's two main types of transitions that we'll be looking at, the electric transitions and the magnetic transitions. So these electric transitions are coming from oscillating charges, setting up an oscillation in the external electric field. So basically, it's all about the protons. Whereas the magnetic transitions are arising from some varying current or magnetic moment from the neutrons, and that sets up a varying magnetic field. And we can have a look at these different types of transitions. Again, it's just one process, some initial state going to some final state. It's no different to what we've done before. We can look at Fermi's golden rule for this. So we can get an order of, we can get estimation just from the order of magnitude of this rate by having a look at the matrix element here. That's the interesting bit. We can leave the rest to later. And this should go as E times the radius of this nucleus. So it depends on the size of the nucleus. And in fact, if we have a look at the decay rate here using Fermi's golden rule, we find that it goes as the energy of the gamma ray cubed times the radius squared. And this is coming from substituting alpha in here for our constants, Z and H bar, etc. here. So what does this mean, though? What does this mean? We're talking about electric dipole transitions. We have a 1 MeV photon typically and a 5 femtometer radius nucleus. That means that the transition rate here for this electric dipole transition, we can plug those numbers in for this basic estimate of the rate. It should be happening about 10 to the 16 times per second. Very, very, very quickly. Very, very short decay rates. So with these electric dipole transitions, they're happening very, very quickly. We know that the photon has L equals 1. It's carrying away some orbital angular momentum, and that means it's going to change the parity of the nucleus. The initial state and the final state are going to have different parity. So it's going to go even to odd or odd to nucleus. Sorry, even to odd or odd to even. So these electric dipole transitions, just by having a look at the dipole matrix to get a first order estimate of this rate, we can say that they happen very quickly. The decay rates are about 10 to the 16 per second, and they're going to change the parity of the nucleus. There are electric dipole transitions, E1. So next, let's have a look at the magnetic dipole transitions. So again, it's the dipole transitions at L equals 1. And instead of the electric dipole matrix element that we had a look for slide 31, we're going to plug in the magnetic dipole matrix element. So here we've got the magnetic moment mu acting on the Pauli spin matrices. Now, typically, let's get rough order of magnitude estimate here again for this matrix element. This should go roughly as the nuclear magneton. And so what we're interested in here for a proton, h bar over the proton mass should be about 0.2 femtometers, which is for a 5 femtometer radius nucleus about r over 25. Now, we're not going to get into this too much, but what we can do is just compare this rate. We're going to normalize it to our electric dipole moment here. So here we know what our typical magnetic dipole matrix element should look like. Remember, these decay rates go as the matrix element squared. So we've got our factor of, we've got our raising it to a power of 2 here. And we've got our electric dipole moment here squared, the matrix element for that coming in for E1. So we compare these rates, we normalize one to the other, and we should have roughly an order of 10 to the 3 between them, 3 orders of magnitude. So these magnetic dipole transitions will take about 1,000 times longer to happen than the electric dipole transitions. They're slower. Their decay rates are larger, about 1,000 times larger. Now, if you have a look at the magnetic moment and see how that transforms, it transforms actually the same way as our angular momentum here. So here we have a parity change here for R and P. If you remember, I'll just flick back when we had a look at the parity change between this electric dipole transition here. It just depended on R, and so when you change the parity, the sign of R flips. If we do the same thing here, we've got ER cross P. Both R and P are going to flip sign under parity, and therefore they're going to cancel one another out, and there will be no change in the parity of the nucleus. It transforms in an even way under parity. So when we have these magnetic dipole transitions, not only do they take 1,000 times longer to actually happen, so they're a lot slower, the decay rates are larger, smaller, no, they're smaller. These transitions don't change the parity of the nucleus, whereas the electric dipole transitions do. And let's have a quick look at these higher order transitions where the photon, the gamma ray, takes away more than 1 unit of orbital angular momentum, so where L is 2 or more. So what we can do, these kind of photons, when they're carrying away more than 1 unit, are called higher multipole radiations, i.e. when you have different parities of your photon based on the L values. So let's have a look at our Hamiltonian from this photon exchange. This is just electromagnetism, right? We can have a look at it in terms of its vector potential, A here, acting on the initial state to the final state. And we can have a look at the wave function for this vector potential, and we can expand it. It's just got simple plane waveform. We can expand it in increasing terms of P dot R, the momentum dot with the radius. So we've got P dot R there, P dot R squared, etc., etc. The first term is what we're going to take as our dipole expansions, whether they be electric or magnetic dipoles. The second one is where L equals 2, so L equals 1 here, and L equals 2 for the increasing order of our transition. And these are our E2 and M2 quadrupole transitions. And then going up one for L equals 3, we've got our octupole transitions here. And you can see that we're increasing in a factor of P dot R each time we go up a successive term. Now, we can compare these higher order terms to the lower order terms that we've had a good look at here for E1 and M1. If we do this, let's have a look and compare the quadrupole transition, quadrupole electric transition, to the dipole electric transition here, E2 to E1. And if we do that, we'll find we've got an additional factor of P dot R, which gives us roughly P dot r squared in our matrix element, which we know is about 10 to the minus 3. So that when we compare the decay rates between E2 and E1, we've got an additional factor of PR squared here, which will suppress this quadrupole transition with respect to the dipole transition by a factor of 1,000. And this is similar to what we saw for the M1 to E1 transitions here. So every time we go up a unit of orbital angular momentum here, we are going to decrease the decay rate of that decay, and the E to the electric versus the magnetic decay rates at the same order of L here, we are going to also have a suppression of a factor of 1,000 as well. Okay, so let's summarize these gamma ray transitions here. We've got the two types, the electric transitions and the magnetic transitions. We had a look at the electric dipole transitions and the magnetic dipole transitions and the higher order ones as well with respect to the lower order. For our electric dipole transitions, we saw that there was a parity change, and we're going to normalize everything with respect to these transitions here. So our E1 transitions of rate 1, we did see a parity change, and the spin parity of the photon that's emitted is spin 1 negative parity. If we have a look at the magnetic dipole transitions here, we saw that there was no parity change, and there's roughly this factor of 1,000 difference in the rate for the transition here. So that's why it's sitting in this column here. And the spin parity of our photon here is it's spin 1 and even parity. The electric quadrupole transitions we saw again, we're going to put them in this column here because they're 1,000 times, the decay rate is 1,000 times smaller. It doesn't offer any parity change because we are changing parity there twice, flipping it twice for the radius, the ER. And the spin parity of our photon is 2 plus. And we can go on and on up here. So our magnetic transitions are offset by a factor of 1,000 with respect to our electric transitions. And they offset nicely with parity changes as well, whereas E2 and M1 offer no parity change together, but the spin parity of the photon emitted is different. So in general, like with all decays, a decay is going to uh, the decay that's going to dominate is going to be the one that is fastest because it takes less time to happen. So if an E1 decay can happen, it will happen in preference of an E2 decay. If an E1 decay can't happen, the one that will dominate is the E2 decay, etc. So, for example, if you had a process where the difference in the spin of the initial and final states, the excited and the ground state, for example, is 2, there is no and there's no parity change, we would be sitting here where you could go via the E2. That will give you a delta J of 2 and no parity change. Although you can, of course, have M3 and E4. You can have a delta J equals of 2 if our photon is spin 4 positive parity or spin 3 positive parity. Write down those quantum numbers and see if you can prove that to yourself. So these ones are also allowed, but they are very much suppressed with respect to the E2 transition. Oh, there you go. Right. So let's have a look at this in terms of tin 117. So I'll just switch here. I'll just switch here and add a page. So we're looking at tin 117. Not that that matters at all, actually. We've got tin 117 here on slide 35, and it's got some particular energy levels, and we want to have a look at which ones are allowed and which ones are less likely. So we're told that the highest energy level is 7/2, spin 7. So this, I'm talking about spin parity with this typical notation that we have. The highest energy level is spin 7/2, even parity. The second highest is 11 over 2, odd parity. The first energy level there is 3 over 2, positive parity. And the lowest one is a half, even. So what I'm going to do is have a look at these possibilities here. I'm going to have a look at the 3 over 2, even parity, going down to the half plus here. So I'll try and use different colors for this to make it easy. So we've got 3 over 2 half, sorry, even parity going to a half plus. So there's no parity change. And that's nice. And we also have a delta J of 1. So if you go back to, for example, slide 34 and you have a look at the table and what's allowed there, we've got no parity change and a delta J of 1. We want the M1 transition. That will give us no parity change. There we go. That will give us no parity change and it will give us a delta J of 1 because the spin parity there for our photon is 1 plus. The next one I want to look at, let's do in dark green here, is 11 over 2 down to 3 over 2 here. 11 over 2, negative parity, odd parity, going to 3 over 2, even parity. So here we have a parity change. We know that. So we know what columns we'll be looking at, E1, the E3, etc. We've got quite a large change there, a delta J of 4. So if we sort of go along our columns on slide 34, we don't actually have a column for this, but you can extend it. The one that will give us a parity change and a delta J of 4 is going to be the M4 transition. And that gives us a spin parity of 4 and odd parity for our photon. I'm running out of colors. How many have I got here? I'm going to draw another. So we said M4 here for this one. I'm going to have a look at another decay all the way down to the half plus here. So 11 over 2, odd parity, going down to spin half, even parity. We could have that transition as well, couldn't we? And here we've got a parity change. Same as before, but this time our delta J is 5. Right, so what can we have here? We could have an E5, but actually that's less likely than M4, actually. So we could have this E5 transition. Where is that going to sit? That's going to give us, with a spin parity there of 5 minus. But actually that's this is much less likely to happen than the M4 parity. Less likely than M4. So maybe we should do that kind of dashed here. So this transition here from the 11 over 2 state all the way down to half plus would happen via an E5 transition, which is actually less likely than this M4 transition. Okay. So if a nucleus is sitting, an excited state of tin is sitting in the 11 over half odd parity state, it's more likely to go down to the 3 over 2 even parity state and then via an M1 to the ground state rather than straight to the ground state. Right, now let's look at the highest energy level and what it can do here. We've got 3 possibilities down to the 11 over 2 state, down to the 3 over 2 state, or all the way down to the bottom here. So we're starting off with 7 over 2, even parity. We're going to have a look at 11 over 2, odd parity. So this first one, there's a parity change. And we've got delta J equals 2. We can have an M2 transition there. Let's have a look at the one a bit further down. 3/2 even parity. There's no parity change here now. And we've got a delta J of 2. Oh yes, of course, in the other direction. So this can give us, we can do this with an E2 transition. And finally, we're going to have a look at the decay all the way from this top level, 7/2, even parity, down to 1/2, even parity. And again, we've got no parity change. And we have a delta J here of 3. So we're going to have an M3 transition here. So when we have a look at what's likely here, over the M2 will obviously be more likely than M3, and our E2 transitions are more likely than the M2. So it's our E2 transition here which will dominate, and we can draw the other ones with dashed lines because they are suppressed. So we can sort of use these transitions and what's allowed and what dominates, so that, for example, on the if we have the most excited state here, 7/2 state of tin, it will drop down 2 energy levels, and that will dominate over any of the other possible transitions, and then decay via an M1 transition to the ground state. If we're sitting in the second highest energy level, it'll undergo an M4 transition to the first energy level and then drop down to the ground state via an M1, rather than dropping down 2 energy levels at the same time. Okay, so really there's 3 that are dominating here. Right, let's switch back to the slides. Okay. So this summary table on slide 34 is quite nice to understand what rates dominate and why, and also the parity change and the delta J that we could have. All right, so for all of these rates that we've discussing for the gamma ray decay rates, um, they are pretty simple and straightforward. There are many other textbooks that will take into account more collective effects, for example, that are quite important if quite a few of the nucleons are participating in transitions. That's something that we haven't had a look at here. Or if we've got a very deformed nucleus and we've got a large electric quadrupole moment, like sodium, for example. And there we've got our rotational excitations there are actually going to enhance our E2 transitions over the others. So those are quite interesting, and you can have a look, of course, in other textbooks if you'd like to go beyond this course. Okay, so to summarize this long lecture here that I usually take 2 hours to do, and I hope we're roughly within 2 hours. We had a long look at a quick look, sorry, at radioactive decays and dating. So we had a look at how we can date rocks. We had a look at how we could date organic matter as well. And then we started to dig into how we can explain what we see with alpha, beta, and gamma decay. And do remember, this is what we say in the beginning, that the nuclear physics is very complex because we have a lot. It's a many body problem, and we need to use a semi-empirical approach. So we're really looking at the data and seeing how we can try and understand that with the physics that we know. So for alpha decay, for example, we treated this as a simple tunneling problem. That alpha particle already exists in the wider, larger nucleus. It already exists, and it tunnels out through that Coulomb potential there. And through the Geiger-Nuttall law, we could calculate a Gamow factor and understand that strong dependence between the half-life and the energy released in the interaction. Then we had a look at beta decay, and there's 3 types, remember. We've got beta plus, beta minus decay, and electron capture. We had a look at the stability, where it tries to minimize the mass of that nucleus versus beta plus or minus decay, getting into that stable minimum. We had a look at treating beta decay as a 4 fermion contact interaction using Fermi theory. We had a look at calculating uh, we had a look at calculating the decay rate here, and we're talking about a three body final state. So it's a bit more complex with respect to what we did in chapter 2, but nevertheless, we can have a look at the density of final states there, which will give us a good start on the way to Sargent's rule that I know many of you have been asking about. We had a look at comparative half-lives and the selection rules. So we've got those two types of decay, Fermi or Gamow-Teller, and then we have the allowed decays when the electron and neutrino are emitted with L equals 0, and higher level forbidden decays where they're emitted with L larger than 0. And finally, we had a look at gamma decay. We had a look at dipole and quadrupole electric and magnetic transitions, and we normalized everything to the ones that are the fastest, the electric dipole transitions, and we found these orders of 1,000 in the rates between them. We had more and more suppressed as you go to those higher orders of L, which gives us our selection rules, and we had a look at the example of tin just there. Okay, so we've got one more lecture left, which is chapter 16 on fission and fusion, and I'll be recording that in the next few days. Thank you. Bye bye.